So in this problem we got a spring with a spring constant of 22 newtons per meters. Then it says it's a stretch from equilibrium to 2.9 meters. So the question is, how much work is done in the process? Okay, so we got a few things going on. We have the K is equal to 22 newtons per meter, and the distance we represent as X being equal to 2.9. We also know that when we stretch the spring, there's two forces, one opposite that's going to the left and one that is going to the right, so we can stretch the spring. Of course, the force that's going to the right is going to be much bigger than compared to the opposite force that's going to the left. Another information is that this is going to be a constant velocity. So we represent the force as negative kx. In this case, F is going to be U. But what is U? U, or in this case, delta U, negative delta U, is going to be the work of the spring. But we need to find the work of the force that is stretching the spring. So it's going to be positive delta U. Now the work, the formula comes from the work being the F times the displacement. And F we can represent it as kx, as we saw up here. And then we just multiply by delta x. So we can get x times kx divided by 2 being equals 1/2 kx squared, which is the formula that we're going to use. One other thing before we proceed solving the problem is that the x is going to represent, let me show you, the x right here is going to represent the base of the graph that is right here. So the work is going to be the area of this curve. Kx is going to be this arrow right here represented, and the displacement is just pretty much the base. So we could say that the work is equal to the base times the force divided by 2. So that's how we got the x that represents the base, the force being kx, and we just divided by 2. Now, as we just plug in the values, we can say 1/2 times 22, which is the force, times 2.9 squared is going to give us around 92.51 joules. So that's how we say that our answer is going to be 93 joules, letter A. So this problem is pretty easy. It says how much work must be done by frictional forces in slowing a 1,000 kilogram car that is going 26 meters per second to rest or 0. So one thing we should know is that the work is going to be equal to the force of the friction times the displacement, in this case delta S. In this problem, the force that is going to stop the car and it's going to make it to be at rest or velocity equals 0, it's going to be in the opposite direction as the displacement. So it's going to be opposite. That means that the work that is being done has to be negative. So we can also write the work being equals to the change of kinetic energy, or the kinetic energy of the final time minus kinetic energy initial. As we know that the final kinetic energy is going to be 0 at rest, we just have negative 1/2 the mass times velocity squared. Then we have to plug in the values. We have negative 1/2 times 1,000 times 26.1 squared, and that should give us around 340,605. But then for the answer in letter A, it's written in scientific notation. So our answer would be 3.41 times 10 to the 5th joules. Being that the force required to slow the car of 1,000 kilos to be at rest at velocity 0.